Hello. My name is Louise Chawla, and I'm a professor in the design program here at CU. And I'm here to introduce Debra Simmons today because I'm the person who introduced her to Andrew Hamilton. And because he's speaking for the American Physical Society right now at the same time, he could not be here, but he will see the recording and he will connect with you later on today. So the way that I came to know about what Debra Simmons does is that one of her avocations is family history, and she has an aunt who happens to be my neighbor in South Boulder. So Debra was coming up frequently to work on family history together with her aunt. And when I learned what she spent her life career doing, I thought, well, my first thought was, wow. And my second thought was that there are definitely going to be people here in the Department of Physics and Astronomy who would like to hear about her experience and her really career-long work in engineering, and especially her 25 years of work on the James Webb Space Telescope. So let me share her bio a bit, and then I will turn it over to Debra. She's a retired aerospace engineer. She spent 41 years at TRW and Northrop Grumman Corporation working in systems engineering, satellite integration and testing, software engineering. This is attitude control subsystems. That is correct. Okay. Because I'm a social scientist, so I think of something else when I read attitude. Okay. And Orbital Operations. Half of her career was dedicated to the James Webb Space Telescope, and she retired as the Chief Systems Engineer on that program. She served in other leadership roles and was a key member of the team that defined the James Webb Space Telescope Observatory concept nearly a quarter of a century ago. She shared with us as her neighbors that she was at the table when the engineers first sat down with the physicists and astronomers and said, what do you want to see? And then took it from there. So James Webb Space Telescope is the successor to the Hubble Space Telescope and is 100 times more powerful, and you probably already know that. It is 7 tons of fragile hardware operating in the near and mid-infrared wavelengths. The amazing images of our universe that it has been capturing required many engineering feats. In her talk, Engineering at the Extremes, Debra Simmons describes several of these engineering extremes and the science that drove them. She earned her Bachelor of Science degree in Aerospace Engineering from San Diego State University and her Master of Science degree in Electrical Engineering from the University of Southern California. She grew up and attended high school in San Diego and now resides in Palos Verdes, California. So we're very fortunate to be able to take advantage of her being here in Boulder today. And with that, and I have to excuse myself. I have a 1:30 meeting on my side of the campus, so I'll have to leave a little bit early. But I'm delighted myself to be able to listen to you, Debbie, talking to an audience that is much more educated about this topic than your local neighbors here in Boulder. But thank you
so much, Louise. Well, I'll say that I'm probably talking to an audience that's much more knowledgeable about the science that's coming out of this telescope than I am. So I'm not a scientist. I am an engineer, and as much as I love engineering and appreciate all the engineering feats that went into this program, I am ecstatic when I hear scientists talk about the data that they're seeing and getting from this telescope. So I love nothing more than listening to the scientists talk about how happy they are and what they're seeing, what they understand, what they don't understand. So I'm hoping you appreciate the engineering as much as I appreciate the science. So I'll start. Louise gave you a good introduction on my background. I'll touch on a little bit more. And then just so we all have the same understanding, I'll go through just a brief description of JWST, of the observatory, and then talk about, I pulled together a handful of different engineering feats, and really, hopefully you appreciate the science behind them and what it took to get that science now that we are getting. And then just a little bit of current status, but again, you may be the audience that knows more about what's coming out of this than I do. So if any questions come up like that, I'm going to look to somebody else in the audience to answer them. Okay, so as Louise said, I got my bachelor's degree from in aerospace from San Diego State, which finally got on the map since we made the final. Well, we made the finals this year. Too bad it wasn't a good game. And my master's from USC in electrical engineering, specifically in communications. So while I spent 41 years at TRW and Northrop Grumman, and it was half of my career that I spent on JWST, but getting to that point in my career where JWST came along, and at the time it was called the Next Generation Space Telescope. I started on it back in the late 90s. But before that, I had worked in software development, doing navigation and controls, simulations, orbit dynamics. I ran satellite operations for a fleet of satellites for the Air Force, and then also worked in satellite design, specifically in the attitude controls area. I just did a talk recently, and somebody, as they were reading the bio, said, "Attitude control, are you sure? Is that right? Is it attitude control? Are you sure it's not altitude control?" I said, "No, attitude control is right." And they went back and said, "Altitude control." So, no, it is attitude control. And then systems engineering. And what I really appreciated about systems engineering is that it really drew from all the different disciplines and really required an understanding of all the different disciplines that go into developing a system, a satellite. So I spent within systems engineering doing mission design for different customers. So mission design, like starting with what kind of orbit, how many satellites do you need, where do they need to look, how do they need to operate, and spacecraft systems engineering design specifically. And so when I first started on JWST, I was the lead spacecraft systems engineer, so engineering the bus that's actually going to control the entire observatory. And I was also the spacecraft manager for a while. And my last position on JWST was as the chief systems engineer. And what that was is I was responsible for the entire systems engineering at Northrop Grumman for JWST. So I had the experts, the lead engineers, the lead thermal engineer, the lead mechanical engineer, the lead controls engineer, alignments engineer, fault management engineer. So the entire spectrum of engineering disciplines, I had the leads for each of those different disciplines. So it really was the entire breadth of the program there. And my COVID picture, when I wasn't able to get a haircut, just before the satellite was folded up and launched. I'm pointing at the wrong direction. So let's start with what really drove the requirements. So the mission requirements. JWST, they told us, okay, we want to build a telescope that can see 13.5 billion light years away. We want to understand what the early universe looked like, so we need to see that far away, and then how galaxies evolve over time, the life cycle of stars, and looking for other worlds, other exoplanets. And so what this meant was that JWST had to be very large, very cold, very stable, and very precise. So just like any telescope, you know, if you're going to look at something, the bigger the aperture, the further away you're going to be able to see. The more precise that optic is, the better resolution you're going to have. So the more you pay for that telescope, probably the more precise it is. And if you've got a ground-based telescope, you know, if you can keep it from moving, jittering, keeping any outside disturbance, you're going to get a better resolution. And then the cold is obviously infrared. If you're looking for heat signatures, you want that telescope and those instruments to be ultra cold. So some of the engineering challenges that are extreme engineering, the handful that I pulled out, largest telescope ever built. We'll talk about that a little bit. Near perfect mirrors and support structure. A tennis court-sized sun shield to be able to provide the very cold temperatures. And pointing control that is able to place a specified object on a specified pixel of an instrument. And the near-infrared spectrometer, I find this instrument particularly fascinating from an engineering challenge standpoint, and I'll describe why. And then getting all of that, getting it folded up and secure, and all this very fine, very delicate, very precise instrument to be able to withstand a launch. So those are the handful of challenges that we'll talk about here. So again, just comment so everybody understands. The JWST was a collaboration between NASA, the Canadian Space Agency, and the European Space Agency. And Northrop Grumman, so the company that I worked for, was the prime contractor for JWST. Right now, the Space Science Telescope, y'all probably know this already, operates the observatory, and then our instruments that we have here. And the observatory itself comprised of the instrument module, the primary mirror telescope, the secondary mirror out at the end of the tripod, our 5-layer sun shield, our itty-bitty spacecraft bus here with some of we have the antennas, star trackers, and then a little momentum flap out here. And then back here, your edge on, you see our solar array. Okay, so the orbit. The orbit is one of the things I found just so fascinating early on. And the reason is that it's because it enables continuous science. And unlike an Earth orbiting observatory such as Hubble, on JWST, every single moment is a potential science moment. So the second Lagrange point is in the two-body system of the Sun-Earth. The second Lagrange point is on the midnight side of the Earth, about a million miles away. And it is, of these, there are, the unstable equilibrium points are, these are all equilibrium points. L4 and L5 are stable equilibrium points, meaning if you put something there, a force acts on it to move it away, it's going to want to drift back there. L2 is an unstable equilibrium point, so if you have a satellite there and you have a force acting on it, it's going to take some control, some fuel, propulsion to be able to keep it in that orbit, to keep it at that point. But what the orbit is it's actually an Earth orbit and a Sun orbit. So it's actually going around the Earth once per year. So it's going around the Earth at the same rate the Earth is going around the Sun. But it's not precisely at the L2 point. And the reason is because if it were, it would be in perpetual shadow, which means you've got to have battery, a battery pack to be able to last a lifetime. So we rely on solar power, so we are in continuous sunlight. So we actually orbit about the second Lagrange point. And the way that happens is it's actually not at the point, but if I'm the sun and let's say the Earth is here and JWST is here, it actually starts kind of above, or let's say that I'm the Earth and here's the satellite, and it goes down and up and down and up. So over the course of a year, it traces out like the edge of a Pringles potato chip, some perfect up-down pattern. So if you were able to stay at midnight on the Earth all the time and look up in the sky over a 6-month period, the observatory would appear to make an oval, a circle in the sky. And over the course of a year, it makes 2 of those circles. So it's orbiting about the sun, kind of doing that very same thing. But it's in continuous sunlight, and but from a communication standpoint, we need antennas around the Earth to be able to communicate with it. So we use the Deep Space Network, NASA's Deep Space Network, for communications. And again, every moment is a science moment. So if you look at JWST there, it can look anywhere. It can't look toward the sun, and it can't look directly away from the sun. But it can look 5 degrees toward the sun and up to 45 degrees away from the sun. So if you think about it, it can look anywhere in the toroid that's formed around that line back to the sun. So over the course of 6 months, that toroid rotates around, and over a 6-month period, you have access to the entire celestial sky. But you do have continuous viewing at the poles, within 5 degrees of the celestial pole. So great orbit from a science standpoint. Excuse me. Okay, so some of these things, I'm sure some of you are already familiar with some of these stats, but we have built the largest space telescope, 6.5 meters in diameter, comprised of 16 hexagonal mirrors, and each mirror is controlled in 6 degrees of freedom. So what that meant is, once we launched, you have 18 of these segments that had to be aligned and controlled in order to make it look like one monolithic mirror. So we were able to do that with the 6 degrees of freedom that you see there. We have tip, tilt, and then radius of curvature. So the mirrors you can adjust the radius of curvature slightly so that that entire primary mirror looks like you can't see that they're in segments. 100 times more powerful. The size translates to 100 times more powerful than Hubble, and gold coated to better reflect infrared. So visible light better reflected by silver, such as the mirror in your bathroom, but gold is much more preferable and useful for infrared observing. So near perfection on these mirrors. So in order to build the optic that is giving us these spectacular images, each mirror, the requirements on the mirrors were that it had to be built to an accuracy of 20 nanometers. So try and get your head around what is 20 nanometers. That's really fine. That's really small. So to really understand what that means is if you took each one of those segments, so 1.2 meters flat to flat, and you enlarged that mirror, that one single segment, to the size of the United States, along with all of its imperfections, enlarged it to the size of the United States, that there would be no hill or valley, no bump or divot greater than 3 inches. That's how perfectly these mirrors are polished. And the gold coating on these, about a little over 1/10 of an ounce of gold, and it's about 100 nanometers thick. One of my engineers calculated the amount of gold over the entire primary mirror, and it came out to about the amount of gold in like a man's wedding band. I mean, if you assume it was solid gold, that's about the amount of gold that it took to cover that 25 square meters of surface area. So you've got these perfect mirrors, but the support structure that holds them also has to be perfect. So this support structure, and you see the photograph here, this is a photograph that was taken at NASA when they were installing. This is the very first segment being installed on this backplane. And this support structure has the 2 wings that fold back for launch. So those wings have to then deploy and latch into place. So that support structure is holding 2.5 tons of hardware between the structure itself, the mirrors, and the science instrument module that's attached to the back side of the optics. It's holding 2.5 tons of hardware, and it's operating down at minus 400 degrees Fahrenheit, but it's thermally stable to less than 32 nanometers, or about 1/10,000th the diameter of a human hair. So once we launched and deployed, that's how accurately that structure was deployed and is stable. So how do we get the cold temperatures? Most of that is passive cooling. And the passive cooling is provided by the sun shield. This is a 5-layer sun shield that is, each one is precisely separated to allow heat to be transmitted out the side. So what's happening is the sun is hitting the sun-facing layer, and much of that heat is getting reflected, but about 10% of that heat is getting transmitted up to the other side. So then that next layer reflects most of that, and so you get this bouncing effect, and you want to make sure that all of that heat is bouncing out and away from the telescope. And ultimately, we came to the conclusion that 5 layers was the right number of layers to be able to get us to the operating temperatures that we need to be at for the telescope and the science instrument module. So it's a very large structure. Each one of those layers, the 2 sun-facing layers are, it's a 2 mil thick layer of Kapton. And then the last 3 layers are only 1 mil thick. And then they have vapor deposited aluminum on them. The 2 sun-facing layers have vapor deposited silicon on them for better performance. It's less degradation in continuous sunlight, and also charging buildup. From a charging buildup standpoint, the properties are much better. So you've got this huge sun shield that now has to be folded up, tucked up for launch. And that whole system is comprised of, it includes over 400 pulleys, 90 cables, and then it also has some special seaming, because when you think about, these are very, very small or thin layers, and they are going to get hit with micrometeoroids. But what we didn't want was if and when a micrometeoroid hit, that we didn't want it to tear, because the layers are taut so that we get that good reflection property for heat rejection. So you think about that entire mechanical system and all of the things that have to work, have to be controlled. You have to make sure that nothing snags. We don't have cables that are going to get snagged. We don't have pulleys, cables that are going to come off of pulleys. So it's an extremely complex system to be able to get it right. But a really impressive system that's working marvelously. And how good is it working? So we've created a temperature difference of about 600 degrees Fahrenheit. When you look at the hot side, you've got temperatures up over 200 degrees Fahrenheit. And then the temperatures on the cold side, we're getting passively cooled down to like minus 370 degrees Fahrenheit. And the instruments cool down to even further than that. So you've got, over a 600 degree span that exists on the telescope at any given time. I mean, it's one thing to have temperature swings like that, but quite amazing. So the only instrument that has active cooling is the mid-infrared instrument, and that's because its focal plane needs to operate down very close to absolute zero. So it's operating at about 7 Kelvin. So we have a cryocooler on board. What that means is you've got a compressor. That means something that is vibrating, perhaps. So you've got that to contend with. And it also has, so the compressor is housed on the spacecraft side of the observatory. But that means that you've got a line then running from that compressor all the way up, and then the cold finger attached to the focal plane of the mid-infrared instrument. So you've got the cabling, all of those things to contend with from thinking about, keeping this observatory very still, very stable. So anyway, but the good thing with being in continuous sunlight is we also have continuous power. So we do have a battery on board, but that battery was only necessary for the launch phase before we got everything deployed. So precision control. So this is going to the attitude control part of the system. So between the fine guidance, the coarse guidance, the observatory itself, and then the fine guidance, we are able to achieve a pointing accuracy of 4 milliarc seconds, or that's 1/1,000,000th of a degree, which it's that accuracy that says, when a scientist says, okay, I want, that object there, and I want it on this pixel of the observatory, we're able to do that. And the observatory itself is controlled to within 7 arc seconds and is stable to within 1 arc second over a tenth of a second period. So able to point very very, very good attitude control, we'll say. The other kind of attitude control. So the near-infrared instrument is one of the instruments that I find particularly fascinating from an engineering standpoint. So it's comprised, the instrument itself has, this is used to observe objects, the light from objects in order to understand the physical composition of those objects. And it can observe up to 100 objects simultaneously and within like a 9 arc minute field of view. But the focal plane, it has like 280,000 little microshutters. So think about that, 280,000 of these itty-bitty little microshutters that are electromagnetically controlled to be able to open and close so that you can mask out things that you don't want the sensor to see. So each one of those little microshutters is about the width of a few human hairs. And so this is also an instrument that had to survive launch. So you had to prove that this thing, so nothing was gonna come loose, open, be permanently closed. So anyway, I just found that the engineering feat on that particular instrument quite amazing. So all of this has to be then bundled up, all of this very precise, very accurate set of equipment has to be folded up and stowed. And we had 40 deployable structures, so things that actually had to move to get into place. And we had 178 release devices. So things that once it gets folded up, you want to secure it to make sure that nothing is going to vibrate and come loose. So everything was battened down. 178 release devices, and every single one of those had to work perfectly. And it did. The whole deployment sequence took about 2 weeks. And the mirror deployment precision, so once this was all launched and everything was deployed, the mirrors themselves, the primary mirror, was deployed to a precision of about 50 nanometers, or about 1/5000th the diameter of a human hair, after it took the ride. So those are some of the engineering feats, and what I've done is I just put together a couple of my favorite pictures so far. The first one was the photograph that was taken from the onboard camera on the launch vehicle. So this was a picture that nobody was expecting. So we knew there was a camera on the launch vehicle, so that when we separated, the camera was there for visual confirmation that separation from the launch vehicle had occurred and was moving safely away from the launch vehicle. And what we got was this photograph, just the orientation and the sun reflecting. I just thought it was magnificent. But the other really great benefit that many of the engineers were excited about is we had a visual video of the solar array deployment, which happened just a few seconds after launch. So that's something that, of course, everybody's worried about every single deployment, but the very first one is you need to get the solar array out because you need power. Every other deployment, if something happens, you can take time, you can assess what's going on and figure out what to do about it if it doesn't work right. But the solar array, we only had a limited amount of battery power, so that solar array had to get deployed within It was a several-hour period, but anyway, it was great to have that visual confirmation that it worked perfectly. So it was a great Christmas present in 2021 to be able to watch that launch. Anybody here watch the launch? Oh, yay. Yeah, it was, I cried. I don't know if anybody else did, but I thought it was very exciting. And then full deployment was complete by the 8th of January. The observatory is obviously now fully commissioned, and this alignment star, this is the other one that I was so excited to see this press release because, you know, when I mentioned once the observatory is up there and you deploy, everything's deployed, and now you need to align all of those mirrors. And so when they first took the image and they had a target star that they were looking at to use for alignment purposes, so they've got 18 different of those images of those stars. So they have to, you know, they went through a really very well-rehearsed and very well-polished process to be able to align the mirrors, starting with, you know, you look at one, you move it, figure out what, you know, which image that I'm seeing is associated with this particular mirror. And so then you map all those out, all 18 of those images, and then you start to bring all of those 18 into alignment, and then get the radius of curvature just so that it looks like one very beautiful star. And that was the image that said, we've got the mirrors aligned. So then the first deep field image from NIRCam, which, I mean, the deep field from Hubble is a beautiful photograph. This one, I think, even more spectacular and much more interesting. The Carina Nebula and the Cosmic Tarantula with, you know, several young stars never before seen. So anyway, just from a visual standpoint, I think these are spectacular images. I'm sure you all understand much more about what you're seeing than I do, and I appreciate that. But what we have is, you know, from concept to deployment, this really took extremely talented engineers from across the globe, and it's in order to create this engineering marvel. So it's both enormous and intricate, and it's blazing hot and cryogenic, but it's 7 tons of fragile hardware now revealing the mysteries of the universe.
Okay, we've got some time for questions. Does anyone have a question?
Eric.
Hi, thanks for the talk.
Welcome.
I'm curious how the design process was like to test the instrument bay and the spacecraft and the sun shield for micrometeoroid impacts.
Okay, good question. So micrometeoroids, how did we test for micrometeoroids? So part of it were the material selection for many of the components. So we know we're going to get hit with micrometeoroids. Excuse me, the most sensitive component is obviously the sun shield. So we did do testing on different materials to understand how, you know, being bombarded with micrometeoroids, how different materials would behave, and how those materials would behave at lower temperatures, and under, with some amount of stress put on them. So that's where the idea of, seaming, these special seaming to, on the sun shield to prevent, propagation of a tear from going entirely across an entire layer. And the other components, we understand that there are going to be micrometeoroids that are going to hit, and so it's sort of in the design process. You have a lifetime design requirement, and you design for that graceful degradation. So some things aren't immune. I mean, certainly the bigger the micrometeoroid, the less immune we are. But at any rate, it was really the sun shield that got the most attention in terms of extra testing and understanding. Good question.
Be there in a minute.
I said this earlier today, but let me just say it again. Thank you so much for helping build this beautiful telescope that we get to use.
Thank you.
And I want to ask a question kind of on the career side. So we're an astrophysics and planetary science department. We train a lot of astronomers and planetary scientists, and a lot of those folks have interests that are kind of they're not in the aerospace engineering department, but they're bordering on engineering in the sense that they want to be involved with developing new telescopes. And so could I ask, do you have any advice for those particular students, whether that's like grad students graduating with PhDs in astronomy or undergraduate students graduating with undergraduate degrees in astronomy, planetary science, if they want to be involved with building enormous telescopes, what should they do?
Yeah, very good. My first advice, and this is to anybody, I don't care what area you're in, is to make sure that whatever you're doing makes you happy. So if you're in a course of study, if you're in doing some research and you're either bored or it's not fulfilling, then look to do something different. If you think you're interested in something different, do some research, go talk to some other people in that area, understand what their day job looks like. Because even engineering, not every engineering discipline is created the same. So there are engineers that will go into one particular discipline and go very deep into that discipline. They'll become the expert in that discipline. But it's probably because that's the discipline that really excites them. Or they really appreciate being the expert in that particular field. And we need those kinds of engineers. We also have engineers, that, and I consider myself in the latter category, which I'm not real good in any specific engineering discipline, but across a breadth, I understand how an entire system works and the interactions between different engineering disciplines, and the different kinds of engineers that it takes to build a system like this. So you need design engineers, you need test engineers, and all of those are still engineering disciplines, so the people that we need to help test these aren't just technicians, but they are engineers. So a lot of different opportunities throughout sciences and throughout engineering, but take the time to find the thing that makes you happy. So that's my best advice.
We have another question up here.
Yes.
So with Hubble and the stuff that needed to be done in terms of repair, and a lot of the things that we read about in the prelude to James Webb was it's going out to L1 and you can't do anything once it's out there in case something's wrong, and there were 178 mechanisms and all that stuff. So I was just wondering, in terms of the ConOps, why was it ever pursued to have all the deployments happen in Earth orbit and then have it pushed to L1? Was that ever one particular way of doing it? Because I haven't come across anybody who said that was potentially a way of doing it, because that would have given you some insurance for in-orbit troubleshooting before you pushed it out.
Yeah. Let's see. I was never in any conversations where that came up. That's a marvelous idea. But and then the trade-off is now you need a propulsion system that is pretty sizable. You need quite a bit of fuel to be able to now propel yourself and get yourself out into that transfer orbit. So, you know, perhaps different types of propulsion. So now you're looking at different system complexities. But those are the kinds of early questions that need to be answered so that you can start developing the requirements for your system. But what we did is, let's see, we were very conscious of the fact that this was not a serviceable mission. Humans have never been beyond the distance of the moon. And we knew that it had to work right the very first time. So that was really the focus that we took. So from a design standpoint, you know, our propulsion system is very straightforward, no new technology required. And if you think about the amount of new development that was required for this program, that was one of the early philosophies is we've got a lot of development to do for our mirror technology, for testing, for the instruments, and for the sun shield itself. We had never built anything like this. So we knew we had areas across the observatory that were going to require investment and some sort of development. So one of the early philosophies was that the spacecraft, we understand how to build spacecraft, so that is not where we want to invest new technology. So, you know, that kind of might help answer some of the questions, but it's a wonderful idea, and if you've got something that might be a little bit smaller, that might be a really great option. Yeah, nice.
Yes. How long is this is supposed to be last and work, and how long could it last? And then what are the biggest risks of a shortfall? I mean, maybe fuel or micrometeorites or whatever.
Yeah, good question. So the design life was 5 years, but propellant we needed to load enough to last at least 10 years. 10 years of operations. So that was over and above the 6 months that it took for commissioning. So, and right now propellant is the life-limiting factor right now. We have redundancy on all of the instruments, all of the avionics. So right now I've heard projections, some pretty encouraging projections that I've seen or heard some of the experts talk about. I think that somebody mentioned, did anybody see the 60 Minutes episode from a couple of weeks ago? I think they mentioned, I think maybe it was Matt Mountain that cited a projection that I thought was something on the order of perhaps double that. So it looks like a very, very long life, which is really great, seeing what's coming out of this. Yes, Erica. Uh-huh.
Party on today. So how long did you need to fill the systems engineering role after launch? So what was your role in troubleshooting, in commissioning, in preparing operators to be able to do troubleshooting, well into normal operations?
Yeah. So I was fortunate enough to retire. So, but actually, much of my career I spent doing launches and anomaly support. So it was early on, we started rehearsing and doing training and it was not so much now. I mean, now that we're in regular operations, there are far fewer things that can go wrong. And if something does, we've got time to sit back, figure out what's wrong and what we can do about it. But it was during that, the deployment phase was the first one that, we practiced many, many scenarios. So, a lot of us that were experienced in orbital operations and in anomaly resolution would come up with scenarios for different problems and then run simulations and have the entire operations team in there, trying to A, detect that there's a problem, and B, figure out what to do about it. So it was mainly rehearsing for that actual deployment and commissioning time frame.
Well, I have another question, kind of unrelated. So next big observatory, at least, a decade, most likely multiple out before it launches, and at least another decade before it actually goes into like true development. So are there systems in place to document, consolidate, and make searchable lessons learned from JWST throughout all of its development, and then also, operationally? Because pessimistically, it can be an entire career's length between when lessons from operational JWST stuff will be applied to whatever the next observatory is. Are there systems being designed or put in place to sort of safeguard against the loss of knowledge?
Excuse me. Yeah, that's a really important question. And when you start on any project, I think looking back at past lessons learned is always important. And NASA does a good job of documenting. I don't know the exact system that they've used, but NASA has a very good memory of lessons learned. And those are things that work right and things that didn't quite go like they were supposed to, and what would we do different next time.
Thank you.
I think we may have time for one more question.
Could you talk a little about the dynamic range of the instruments? That is, the range between the dimmest object you can detect versus the brightest object you can tolerate without damage?
No, but maybe there's somebody else in the audience who might know the answer to that. Yeah, I'm not a scientist, and I'm not an expert on the instruments themselves, so sorry. But great question.
And if we all just want to thank Debra Simmons for coming today, and
thank you, Robin.